Today's lesson is going to focus on single displacement reactions. Single displacement reactions are recognizable because you'll always have an element reacting with a compound. So in your reactants, you're going to look for an element and you're going to look for a compound. And notice that those are the only two reactants that you have. Whatever your element is, it's going to replace its similar element in the compound. So for example, if you have a metal element, it's going to replace the metal in the compound. If you have a non-metal element, it's going to replace the non-metal in the compound. So here is a general reaction. And when I look at that, I recognize right away that this is the type of single displacement where this A element is a metal. And I know this because it is kicking out B of this compound. And we know that whenever we have compounds, we always list the metal first and then the non-metal second. So you can have this general reaction as one option, but you could also have the same type of reaction, and we'll set it up like this, where if A was a non-metal, then it should be kicking out the corresponding non-metal. And so you'd have C by itself, and then you'd have your metal B combining with that non-metal element of A. So just note that there are two different options here depending on whether your element is a metal or a non-metal. When you first learned about single displacement reactions in grade 10, we always assumed that these reactions occurred. And anything that we had you try in class, or if we did a demonstration, they always worked. There are limitations to single displacement reactions. So the reactions do not always occur. And the only way for you to know if the reaction will occur or not is you have to consult an activity series. So I call it an activity series. Some people call it a reactivity series. It is essentially a list of elements that are ordered from most reactive to least reactive. And when you consult this activity series, the point of that is to determine whether that single element that you have has enough energy or potential energy to replace the corresponding element in the compound. So if your single element is of low reactivity, it is generally not going to be able to carry out a reaction. It will not be able to displace the element of higher activity in the compound. So let's look at a few reactions here. So here's one single displacement reaction where we take sodium and we're going to react it with copper 2 chloride. So before you start writing out your products, you want to check out whether this reaction will even occur. So we're after sodium. We're after sodium and we're after the element copper. And what we want to do is go to the activity series and we want to find sodium on the activity series and we want to find copper. If sodium, who is the single element, is higher in reactivity than copper on that activity series, then we know this reaction will occur. So take a second, find the two elements, and notice their placement. You will notice that sodium is higher than copper on the activity series. So what we know is going to happen is this reaction is going to carry on to completion. You're going to end up with sodium chloride as one product, and then you're going to form copper as your other product. So we can go ahead and write out the entire reaction now using chemical formulas and always to finish balancing it. So let's go ahead and do that. So sodium is Na, not a diatomic, has a state of solid because it's in the elemental form. Copper 2 chloride will be CuCl2. And here is something to note, so make a note for yourself. In a displacement reaction, any compound has to be dissolved in water. So they all have to have the aqueous state. Otherwise, you cannot have a reaction occurring. In the solid state, those two ions are bound too tightly to each other. And sodium does not have the ability to break apart those ionic attractions. So we have to dissolve those solids in water in order to free up the ions. Then we move along and we kick out copper, and sodium and chlorine are going to form a new compound. Remember, go and look up the charges on each of those. They both have charges of 1, and then we will have copper remaining as a solid. Take a look to see if you need to balance it, and you do. You need 2 chlorines right here in front of sodium chloride, which means I need a coefficient of 2 in front of sodium. Let's look at the next example. So here we're going to try to react copper with magnesium nitrate. So again, we are only interested in the element copper and then the element magnesium, and we need to see where is copper located on the activity series. If he is higher than magnesium, we're going to have a reaction. If he is lower, we will not have a reaction. Copper will not have enough reactivity or potential energy to kick out magnesium. So go and look up their locations on the period or on the activity series. And when you find both of them, you're going to notice that copper is lower, okay, lower on the activity series than magnesium. So you are not going to have a reaction. And this is what you write. You write no reaction, which is our short form for the word. And don't write out products, okay? Don't write them out. Because if you do, you're assuming that you're making them, okay? And you're not. Nothing is going to happen here. They're just going to sit, these 2 substances, and not have any kind of chemical change in any way. The last example is taking a non-metal. So we're taking fluorine, and we're going to react it with sodium chloride. So now we have to be careful. We have to look up fluorine, but we have to look up chlorine, because fluorine's a non-metal. He's going to kick out chlorine, which is also the non-metal. And on your activity series, you'll see that you have a halogens activity series to the side that has been handwritten. And the halogen activity series just goes in order down the group. So meaning that fluorine's the most reactive, chlorine is next, then bromine, then iodine. So fluorine is the most reactive. He is higher than chlorine, so he is going to have the ability to kick out chlorine and allow this reaction to occur. So let's finish off writing out those products. So we're going to have chlorine sitting by itself, and then fluorine's going to combine with sodium to form sodium fluoride. And then we'll keep going and we'll come up with all of our formulas. Remember that fluorine is a diatomic. It is also a gas. We're going to react this with sodium chloride. Both of those have charges of 1. And remember what I said, if these reactions occur, any compound is going to be aqueous in state. So we'll just write that in. Then we're going to get chlorine being formed. He's a diatomic, he's a gas. And then sodium fluoride, both of those ions have charges of 1, and they'll still be sitting in solution. Let's balance it. So we need a 2 in front of sodium chloride, and then I need a 2 in front of sodium fluoride, which also balances my fluorines.